Hi everybody, can you hear me? Is my screen visible and am I audible to all of you?
Yes, ma'am.
Okay, very good. Okay, do you have any question from last class? So in last class we discussed about process, right? The basic data structure regarding process, right? What operating system developer should maintain, right? Should create, right? So today basically what we are going to see in detail, some application programming interface that one should have, I mean, one operating system should have regarding process. Okay, so that is the first and main agenda of discussion for today's lecture. In other words, we will see some process related system call. Okay, and if time permits, we will see how to even how operating system handles system calls, right? And how these are different from uh, simple function call. That we will discuss if we have time after discussing these APIs for process control. Okay. So let's start with a simple question which I think I asked in last class also. The question is, which you also answered me the question. Okay, let me do this. So should a process be able to execute any instruction on its own? That was the question which I asked, right? And the answer which you gave, that is basically no, right? It should not be allowed to execute any instruction, right? Means any means, I mean, all every instruction I'm talking about here. Any means every, all arbitrary any instruction, right? So there should be some check, right? That some kind of instruction, maybe we should not allow process directly to run. Some kind of supervision should be there. For example, we should not allow process on its own to read and write from anywhere, right? So these type of things should be monitored by someone, right? And who is that someone? Operating system is the someone, right? Operating system should handle this, that process should not be able to execute any instruction arbitrarily, right? So if you allow that, then basically what some process might do, it can alter the system configuration totally, right? So you will be in trouble. And it can, as we mentioned in the last class also, it can access unauthorized memory, right? And means it can steal data of other process, right? Means hacking. So this should not be allowed. And it can do some unauthorized IO, right? So this should not be allowed. So that's why, in a nutshell, the answer to this question is no. Means process should not be allowed to execute any arbitrary instruction on its own. Of course, some of the instructions which are simple instruction, right? Those kind of instruction process should be allowed to execute on its own. Other instruction, there should be some supervision, right? And the question is how you are going to implement such kind of things. Means let's say we have a simple C program or something like that. So there are many instructions are there, right? And we are seeing, as we are actually telling, that even writing to IO means if we want to print something on the screen, that is also not permitted, right? So that's some IO operation you are doing, right? So now the question is how you are going to handle such kind of thing, right? That's the big question. How you are going to implement that? This some instructions are privileged instruction. We should not allow programmer or user on its own to run them. Other some kind of trivial thing they can do on its own, right? So how to do that, right? So can operating system on its own do that without the help of the hardware, right? So as I mentioned in the past lecture also, in operating system course, you will see there are many interaction between operating system and hardware. And sometimes if you want to do something, some special kind of thing, if you want to implement, then you must consult with the hardware guys, right? You must give some specification that we need to do that, and you need to think about, okay, maybe this can be done by having some kind of hardware help. Okay, so to implement this, we actually need hardware help. So how to do that? So as we mentioned, right, we would have basically two modes. One mode is user mode, another mode is kernel mode, right? So user mode means there you can execute trivial instructions, and in the kernel mode, some privileged instruction would be taken care by the operating system. And how to distinguish between them, how you are going to implement it via using basically some bit, right? One bit is enough. So in hardware, we will use just single bit to which is a basically mode bit, right? If the mode bit is, let's say, 0, then we will understand that it's a privileged instruction, and we should take care, right? It's a privileged instruction is going on, so operating system should handle this separately, different in some different way. Okay, and if let's say that bit is 1, then it's actually in the user mode. Okay, via using this hardware bit, one can actually implement this dual mode of operation. Okay? This is just one pictorial example of that. And of course, privileged instruction. In fact, the printf, if you see, I mean, of course, you must have used printf instruction in some or other form in your program. So that instruction is also some kind of privilege. It's a function call, right? But inside that, you have a system call. Maybe write system call is there, which is actually, so if you see the source code of printf, right? If you see the source code of C or something like that, or maybe C++ or something, there you will see how they have implemented this function. They have evoked this system call. Okay, so system call, right? So that's the one way to interact between operating system and the user program. In other words, via system call. So system call is nothing but it's some kind of function call only, but they are privileged function, right? So these are basically interface to interact with operating system and the user program. So user program will evoke this system call to do some kind of privilege operation, right? So in other words, so if you have some operating system, then there should have several system calls, right? So the operating system developer should write several system calls. So via using these are nothing but some kind of, you can say these are the interface, right? Via evoking those, one user program can do some privileged work, right? Of course, I mean, there is another important aspect. So via using this system call, for example, write is one system call, right? Any user program can evoke the write system call. So now using that write, of course, one need to check where it is going to write. So that kind of thing, right? I mean, of course, write that system call, one user is allowed to evoke. But it's not that if you are going to evoke one system call, right, that operating system will allow to write anywhere, right? That kind of check itself, I mean, operating system should do, right? Okay, so now, to be specific, for example, what happens if one system call is evoked, you can see via this picture. So, for example, it's just, what should I say, it's illustrative pictorial to have the feeling, right? So, let's say you have one user process. So, it was executing in your CPU, right? Now, when the system call is evoked, then basically some kind of extra thing, as I mentioned, so some trap is happening. Now that part of the program means that system call evocation, that is actually done by operating system as in the kernel mode. Okay, it will execute the system call on behalf of the process, right? Once it is done, then basically it will change the hardware bit. It will change the hardware bit from 1 to 0. Of course, when the system call is happening, this trap is happening, of course, you need to change the bit initially to 0. Once it is 0 means you are actually telling the processor that, okay, you are now in the privileged mode and you can execute certain system call, right? And again, to execute this system call, you need the support of hardware and all. So that how to execute a system call and all that we'll discuss. If today's, I mean, if we had time today, and towards the end of the class, we will discuss that in detail. Otherwise, in the next class, we'll discuss. So once this system call is actually, I mean, this is as it is function call. So it is done, right? Then you need to change that mode bit to 1 to signify now it is going to in the user mode. Then it will return from the from kernel level or kernel mode to the user mode, and the continuation of the process will be going on. Okay, so this is the pictorial illustration when some system call happens. So in other words, what is system call? System calls are basically application programming interface. Okay, as I mentioned already. Right. Right. So these are the function call. That code is actually it's a OS code that runs at a higher privilege level of the CPU. Some sensitive operation, of course, some sensitive operation like access to hardware, those things are allowed only at the higher privilege level, right? In fact, if let's say some process was running, right? Now that some blocking system call is also there to block that. Okay, that process needs to do something else. Maybe we can block the process from the CPU, right? So these are all privileged instruction, and that can be performed via system call. There are particular system calls to do that. Okay, so for today's lecture, we'll see process-related system calls which are available in Unix-like environment. There are many process-related system calls, so we will only concentrate on very basic 4 system calls. One is fork, another one is exec, third one is exit, and fourth one is wait. We'll see, what these system calls are and how to implement such system calls. Means what should be the code of those system calls. Okay, so first let's see what is the fork system call. So fork is basically it is a system call which is the system call to, if you want to create some process, then you need to evoke this system call. Okay, so initially there is one process. You can consider that process as operating system. Like let's say initially you should have one process, right? Let's say one program is you have just started your machine and no application programming is running on, let's say. Then there is one initial process which is known as init process, right? Every other process are basically ancestor of that process. Means if you now want to create some process, you need to evoke the fork system call from this init, right? So that's from that parent process. Then maybe let's say we have some process. From that process again, you can evoke fork to create some other child process. So basically, fork is used to create new child process. So all processes are created by forking from some parent. Okay, and init is the process, as I mentioned, is the process which is ancestor of all processes, right? And what is the purpose of exec? Exec is basically it's a process via using which you can actually, sorry, it's a system call that makes a process execute some executable. Okay, we will see in detail. I mean, what does that mean? And exit, you know, right? This exit system call maybe you have used when you have written C++ program, right? It is actually, if you write exit, then it's actually termination of the process, right? If you want to terminate one process, then basically we use exit system call. Okay, does it make sense? And there is another system call which is actually used for waiting purpose. Means, let's say, as I mentioned in the last class, let's say we have one parent process which actually forked many children, right? And it might happen the execution of the parent is actually done before, completed before the children, right? It might be the thing. Then those children process, when they become dead, their entries in the process list are still there. There will be the process list, right? It's a burden. Who will basically clean up those entry from the list of active processes, right? Though those processes are already dead, but we don't know that. There is no way to clean up those, right? So there should be some mechanism. So it's a good programming. What should I say? Attributes. I mean, if the programmer take care of this, let's say I have created one children, right, in my program. So if the parent process wait until the child dies, then basically before the parent is dead, then it can actually take the responsibility to rip up those entries from the list of process, right, which the operating system is taking care of. So to do that, to enable those kind of things, basically this wait system call is there. It actually causes parent to block until child terminates. Okay. So we'll see all these 4 system calls in detail using some example. Okay. And there is another important thing. So there are many variants of these system calls, means how to evoke these system calls. To see in detail, maybe you can see the Back's book. This would be useful when you are going to write operating system labs programs, right? We have also lab part of it, so that book might be useful. There you need to see the specific function. I mean, this system calls format, right? That we are not that much serious in the theory part, right? So what is the specific format of evoking this fork? There are many variants of it. So we are not too specific to those format. Okay, now let's see the most important and interesting system call related to process, that is fork. Okay, so what is the fork? So now let's see one example. Here, basically, it's a program written in C. Here, if you see line number 9, so there we have written a program where we are evoking the fork, right? So means we are creating a child. Now you see this code of the program. We are seeing that if so this RC is the return value by fork, right? So if the operating system is not able to create a child process, then it will return the value which is less than 0. Okay, means fork was failed. Okay, if that is the case, then in this program what we are going to write, that the fork is held and we are actually terminating our process. Okay, main process. Otherwise, so RC equals to 0. So what is the meaning of this? So as we mentioned, right, fork is basically by using fork you can create a child process, right? So in the child process, the return value of fork would be 0. Okay, so there you are going to actually print that. Okay, you are going to say that okay, this is the child process. Otherwise, we are going to say that this is the parent, and we are going to print both the parent ID, right, and the RC value. So what is the RC value? So in the parent process, the return value of fork is basically the process ID of the child. The process so by using fork, basically we are creating one child, right? So that child process should have one unique process ID. So that process ID will be returned to the parent, right? So if you just print this, then you will see the process ID of the child, the process which you have just created. Okay, so I hope you have understood this simple code. Now the question is, what would be if you run this program, right? If you just compile it and if you make it executable and run the program, then can you tell me what would be the output of this program? How do you expect to see in your screen? Can you tell me? Say I have written the program and I am executing this program. Okay, after compiling, can you tell me what What would you, I have explained all the things, right? So can you tell me quickly, so what you can expect if you run the program? Can you tell me? This is very simple, right? Even if you are not absolutely correct, you can actually guess, right? There is nothing wrong in it. So let's say it's the case that operating system was able to uh, mm, create one child process. Then, so okay, my question is, I am changing the question. Will you see same uh, mm, same thing if you are running this program maybe twice, thrice? Will you see the same thing, same sequence? For example, what you can expect? Maybe you can expect uh, hello, this line, right, with some PID value. Then next line you can expect something like this, right? This might be one possible order, right? Or would you see something different? What do you think? Will you see that hello, then this line will be printed fast, then this line, in case the operating system is successful to create the child? Can you tell me? Or you'll see something random? Okay, this is advisable to write this code on your own and do this experiment on your machine. Okay. So if you do that, then you will see actually the answer which we are getting. So for example, let's say the P1 is the executable which we have created for the this program, right? So if you are going to run it, you will see either this or that. Okay, it's not that you are going to get some deterministic order. It's randomly. For example, you might see that the parent is actually printing its value fast, means hello, I am parent, and it's parent of the child this, and it is going to print its own parent ID, PID, right? And next is basically the child got chance, right? And it is printing the value, or maybe just the opposite. But this is for sure, this line will be printed first. There is no doubt about it, right? This is going to be printed first. Now the question was, which of these two will be executed first? So you might see either of this or that. Okay. If you run your program, you'll see this. So now the question is, why this is happening? Can you answer? So you are not getting any deterministic result, right? If you are going to run this, you will see that you are not getting any deterministic result. It means deterministic uh, order, right? It might be this one or that one. So now the question is, why this is happening? Can you tell? Can anyone tell? So I can see, Dharmendra, can you tell it, illustrate it, why this is happening? Or Khushi, can you explain? I can see, I mean, at least some, I mean, this is very trivial question. Please answer this question first, then we'll move. No worries, I mean, so first of all, did you answer, did you understand what is my question?
Ma'am, can you please repeat the question?
Right. So the question is, if we are going to run this program, right? Then, I mean, the result, whatever you are going to get. Say I have run this for twice, thrice, fourth time. Every time you will not get the same sequence of answer. So it might be the case that in one run I have got this sequence. In another run, I got just the opposite. Means among these last two lines, you can see there is a swap, right? It might be the case that the child got first executed, right? Then the parent is executing, or the other way, right? Parent got executed first, then the child was executed. So my question is, why this is happening? If you execute this program, then either of these two is happening, and there is no deterministic answer, right? So why this is happening? That is my question. Now, Dharmendra, did you understand the question?
Yes, ma'am, I understand.
Okay,
I
so
don't
can you
know
answer?
what is
Oh,
happening.
okay, you don't know, but you understood this programming code. Did you understand?
Yes.
Okay, so okay, good. So basically, what is happening? So when one, so basically, by evoking the fork, right? Here you have evoked fork. So you have created one child process, right? So this, so now we have two processes. One is parent process, another is child process. And which process got scheduled first and which process got scheduled later by the operating system, that we don't know, right? Because we don't know the scheduler algorithm, what is there running on, right? So it might be the thing that, okay, in some execution, child process got the chance first, then the parent got, right, then it was executed by the CPU, or the other way around. So that's why basically it is happening. We have two process now. One is child, another is parent, right? So any one of them may get chance to execute before the other one, right? It's depending upon the scheduler, whatever the scheduler we have. So okay, don't worry about what is the scheduler and all, right? So that we will discuss in detail in next class. Okay. So for the time being, you can think about scheduler is a subroutine which is responsible to schedule which process should be executed and which process should wait. Okay, for some time. Okay. Now let's see if you understood the fork program. I am so sure you have not completely understood it. Okay. So until and unless I gave you some pictorial thing, you will not be able to understand. Okay. So what are the steps to implement fork? Okay. So let's see that first. So first step is, of course, so as I mentioned, so via using fork, you are actually going to create one child process, right? So if I want to implement fork, means in the operating system level, I should have a code for fork, right? And in that code, we should take care how to, create one entry in the process list for the newly created process, right? So in other words, we should create and initialize the PCB in the kernel, right? So we should create one entry, right, in the process list, right? So, and we should initialize it. That should be the first step. Okay. And of course, since this is a new process, we should create a new address space for it, right? So that should be the thing. And of course, if you remember the process and all, so you have you need to load that process into memory, right? So basically, now the question is what you should load right there. So you have created one address space, right? Means now you need to write something over there, right? Now what should you write? So here is the answer. In the fork, basically what we are going to do, we are initialize the address space with a copy of the entire content of the address space of its parent. Okay. All the things whatever you had for the parent, so we are going to copy it in another address space. Okay, we are making two copies. Means we had the one copy for its parent, whatever the memory image we had for it, we are going to copy it for the newly created child process. Okay, so and not only that, so the execution, the inherit, so it also inherit this new process, newly created process, also inherit the execution context of the parent. Means if some files are opened already by the parent process, right? So all those things are also open for this newly created child process. Okay. And after doing all these things, then basically we need to inform the scheduler. So as I mentioned, scheduler is a subroutine which is responsible to make some process schedule to the CPU, right? So you should inform the scheduler also that a new process is ready to run. Okay, these are the steps to implement the fork subroutine. Okay. Okay, I hope, no, I don't have a picture here. Okay, I would like to make a picture over here. So maybe let's do that here. Sorry, not here, here. So the picture is something like this. If you will understand it more easily. So basically, you can see at this moment, basically, we are actually evoking the fork system call, right? Okay, so before that, we had this original process. Let's name that original process as P1, right? So if you, let's say this is the main memory. So there, for this process P1, let's say, original process, I have one memory image already, right? So there we had code, right? Some one part is stack, right? Some part of it is heap, right? These things are there, right? For this process P1, right? And code means instruction, right? So somewhere, okay, so somewhere, and you know the program counter, right? This program counter is actually pointing to this instruction, right? Over there. Now, after completion of this fork, right? So when you evoke the fork subroutine, so if you remember, so we mentioned, so in the fork subroutine, what we are doing, we are creating one entry to the PCB, right? One new, in the list of process, we are creating one entry to that list, right? That is maintained by the operating system in that list. After doing that, what it is doing, it is actually creating one memory space corresponding to this child process. Let's say the child process, name of the child process I am giving as C. Okay. So this is the memory which we are actually allocating in the main memory, right? To that newly created child process. And all the content, whatever you have for the parent process, that I am going to copy. So everything, whatever we had here, so that I am giving it over here for the child process. Okay. And the for example, of course, the next instruction to execute for this child process would be this one, right? Because its status is exactly same as the parent, right? So after revoking the fork system call in the parent also, the program counter should actually point to there, right? And same should be for the child process. Both of them are actually pointing to the next instruction, okay? And the only difference is in the parent process, the value returned by the fork, right? That value is going to be the process ID of the child, okay? And in the child process, the value of RC would be just 0. That's the only difference. Other than that, there is no difference. With this, now the same piece of code, whatever you have for this, that will be actually executed by both of them. Okay, I hope you have understood it. This is so simple. Okay. Okay, now okay. So now if you see this step of execution, right? So let's say this step. So as I mentioned, there could be, it might be the case that if you run the program, it might be the case that parent process got scheduled fast and it completed its execution before its child. It might happen like this, right? And if that is the case, then I mean, there would be some zombie entry for the child process, right? When the child process will be dead, there will not be anybody who will reap or clean up the whatever it is used by the child, that there would be no one to clean up, right? So we want to stop somehow. Here, it is not the case. It might be that the child was actually alive after the parent is dead, right? In other words, it might be zombie in that case, right? We want to stop that. So to stop this, we have another system called, that is basically wait. And if you see, so now we are actually using wait system call. So this program and P1, the program which we just show you before, there is no difference except this line. Okay, so here basically parent is evoking wait system call to indicate, okay, I want to wait until the child is finished his job. Okay, so if that is the case, then basically this parent process will be actually blocked. If child is not completed, then basically this parent process will be blocked. That's the purpose of this wait system call. So once the child is executed completely, then it will actually indicate that, okay, it is completed already. Then this wait system call will take care of that, and it will unblock the parent process. So that's the purpose of wait. Okay. So if you execute it, then always you will see. Okay. Okay, you will see, if you execute it, you will see this. Okay, there is no non-deterministic here, non-deterministic here. You will always get some deterministic answer like this, because before printing this statement, you actually inform the operating system right ways that we want to the parent wants to wait until the child is executed completely. Okay. So that's why you can actually wait the parent process until the child is completed. It's complete execution. Okay. So that's the main purpose of wait. And it is always advisable to do something like this, because if you are not doing this, so now you understand. We might have several processes which are actually dead, right? But their PCB is still there in the with the operating system, right? Means that some memory is actually wasted, right? So in other words, if you are allowing to do such thing for a long time, your system will be very slow, right? Because it might happen that after some time you are actually running out of memory. Okay. So to avoid this, it's always advisable to write your program in such a way that before saying that, okay, this parent process is about to exit, you should wait for the child process to exit. Okay, and that is the main purpose of this wait system call. Okay, good. So I think I have right. Waiting for children to terminate, right? We have already explained all these things in detail. Right. So, but yeah, so that also we discussed in last class. So even if the parent terminates before the child, so there is init process which actually adopts the orphans, and it will reap all the orphans, but it will not do this immediately. Okay. So it will do, okay. So it's again the duty of the operating system developer. So it's a design decision whether the init process will reap of this, orphan of whatever the orphan you have, whatever zombie you have. So when it should clean up, should it clean up, or with some frequent intervals, or before, or something maybe when it is going to be shut down, when you are going to shut down your machine, at that moment you are going to do that. So it can do either of these things. Okay. So, but it's a design decision. You may actually think about to do this. Via using init process, you can reap all these zombie processes after some interval of time, right? So that even if the programmer don't do that, you have a bad programmer, let's say. In that case, also your operating system will not be that much slow. But if you are going to do this frequently, right, then it's a wastage of what should I say? It's a wastage, right? It's wastage of time, right? There is always trade-off. So in how frequently you should do that. Okay. So that those things are basically design decision. Means whenever you are going to design something, some system, right? It's not that hard and fast rule that you need to do it with this much frequency, That frequency depend upon which kind of environment you are going to use your system, right? Depending upon that, you need to make that type of design decision, and you will see this frequently in operating system level. Okay. These are called engineers decision. Okay. It's not like you are mathematician, right? Mathematics plus computer science. So it's not that you have some particular theory that you need to do it after 5 minutes or maybe 5 seconds or 5 milliseconds. There is no such kind of theory. Okay. So these are all design decisions you need to take care of when you are going to design some system. Depending upon, as I mentioned, depending upon its application, where it is going to be used, in which environment your operating system will be used. Is it a home environment or maybe it's a industrial environment, right? So many factors come into that. Okay, now let us see another system call. Okay, so this is another important and interesting system call which behaves, some surprising way. Okay, so I would suggest you to write your own code, and you may change also, right? The sequence of the programming, writing, and all, just to have some flavor about it. Okay, so let's see how you can evoke exec system call. So again, this exec system call, as I mentioned earlier, via evoking exec system call, you can actually execute some some program. Okay, you can execute some program, any program you can say, or some executable rather. You can execute any executable. Okay. For example, let's see this example. So here, basically, all the things which we had for the previous program, same thing is there. Only this is the difference. The difference is here. This is the only part which is added. Okay. Apart from this, you will see everything is same. This is the only extra part. So what is that extra? So, and it's, of course, it's in the child process we are writing this, right? In the child program, in the child process. So this part will be executed by the child, not via the parent process. Okay. So here, basically, you have what you are here. You are executing the exec system call. So there are many variants of exec system call. Here we have just taken one of the variant. There are several variants. You can see exec, exec, d, exec, l. There, this variant is exec vp, right? So in this variant, what we are going to do, we are passing two parameters, right? The first is this, okay? WC stands for word count. This is executable. Maybe you might have used word count in the prompt directly, right? If you write WC means word count, then if you pass some file, then it will give you how many words it has in that file, how many lines do you have, okay, how many characters do you have, all these statistics you will get if you execute WC. That is just one command. Okay. You can use it in the command prompt also. Means if you just write WC, then maybe let's say you pass some file, right? Let's say the file is pitchy.c itself. Then, and if you just enter it, then you will see the number of lines, for example, number of word, number of characters, number of lines, that you will see. Okay, so we want to execute that command via some new process. Okay, new via our new child process. So that's the whole purpose of this new child process. Okay, so for that purpose, we are actually evoking exec system call. Okay, so if you remember, In the earlier program, whatever we have actually shown for illustration, there the child process and the parent process, they are basically identical, right? If they are identical, then you can't do much, right? So what is the purpose of creating a child process? So of course your purpose is to do something different, right? So okay, if both of them has the same identical copy, and okay, of course you can change something in this part, right? Of course you can change it, but you can't do much maybe, right? So via using exec system call, we are actually allowing the child process to be different than the parent process. That's the whole purpose. Okay. Okay, if you just compile this program and if you run it on your own, then you will see, as I mentioned, the child process. What it will do, it will actually take the file p3c and it will count how many lines are there, how many words are there, how many characters are there in that file. Okay. Then since we are actually using wait system call before printing this statement, so parent process will be blocked until child is finished. So that's why you can see the child is completed, then only parent got chance, right? And it is executed. Okay, so now the thing is, so what are the main difference here? So if you are going to execute exec system call or maybe evoke exec system call, what are the difference it might happen in your child process, right? That's the question. So can you think about what could be the change? So you are basically as if you are running some new process, right? Via, I mean, your child process is there. So the purpose of the child process is to make completely different from the parent process, right? So if that is the purpose, you can see. So when you executed for means when you just executed for, after that the parent and child, they had the same code. Okay, so not too useful as I mentioned already. So you want to do something different, right? So that's the purpose. That was the whole purpose. So what exec is doing, it is actually loading some different executable, right, to the memory image of the child process. So earlier the child process had, so until you are actually until this point, so everything whatever the child process had in the memory, right, in its memory image, everything was same with respect to the parent, right? But once you execute this exec system call, then basically the scenario got changed drastically, right? What happens? Then child has a different memory image corresponding to that new program, whatever you are going to run, right? Okay, so that's the main thing. So in other words, there are, I mean, in other words, a child can run a completely different program rather than, I mean, completely different from the parent process, right? That's the main purpose. And there are many variants of exec system call, as I mentioned already. So you can see what are the variants available in Unix environment, okay? And those might be very much useful when you are going to do lab, okay? So maybe after today's lecture only, we can think about one lab question, okay? That we'll see later. Okay, now let's see with picture, right? So picture will tell you more. For example, let's say it was your program, right? So until you fork, so there was only one copy in the memory, right? Before this, so let's say this was the memory. So I had only this memory image were there in the main memory, corresponding to the original program, right? So once you fork, then basically one new image is created corresponding to the child process, right? But everything is same with respect to the parent process. Both of them are same, right? Okay, now when you are actually executing this exec system call, then this whole memory image, whatever you had, that is going to be replaced by the executable, whatever you are going to run via exec system call. So that has some instruction. So it is completely, I mean, that code part is completely replaced by this new code, right? It would have its own stack and all. Okay, so that will be replaced by, right? And the parent process, okay, parent process to, yeah, it was same as before. Whatever the memory image it had, so it has that same thing. There is no difference. Okay, so that's the basically pictorial illustration when you are going to execute exec system call or evoke exec system call in your program. Okay. Okay, another interesting thing is, as I mentioned, right? Okay, let's see this piece of code. So you can see there is one line after the exec system call in the child part, right? This is the child part. So I have written one printf where the child process is supposed to write in the screen that this should not print out. Now the question is, are you going to see this in your screen if you are going to execute this program? I hope you have understood how exec system call works, right? And now the question is, are you going to see this line? This should not print out this information. Are you going to see in the in your screen if you are going to execute it? Any answer? Any answer? No answer. Okay. So if you are not giving me answer, then maybe I need to answer it, right? So you can see we did not see that line here, right? We did not see. So now can you explain me why this is not going to print out? Hetvi, can you answer it? I can see Hetvi, then Adit is there, Kartikeya. So are you guys listening to or doing something else? Any answer? No answer. Okay.
Maybe the exec system call is terminating the whole child process.
It's okay. It is terminating the whole child process. Okay, so it is not terminating the whole child process. It is basically it is replacing, right? If you understood what I just explained, so it is replacing the whole memory image. So the code part, whatever it had earlier, so it is actually replacing that thing. So that is the main reason. So the earlier whatever you had, this code part is not available once you write exec. Okay, this part is completely replaced, means whole part is completely replaced. So this part will also be replaced, right, by new executable, and that executable is basically here, the thing which you are passing to the exec system call, right? For example, WC is your new executable. You have the instruction corresponding to WC, that will be your new code part. So all the codes are going to be replaced. So whatever you write after this exec system call in your program in the child process part, that will not be executed. You will not be able to execute that. Okay, that's the difference. So that's why you should do experiment on your own to see what kind of magic thing you are observing when you are executing these system calls. To be specific, exec and fork, they will behave randomly. Okay, but it's not random. Of course, you can explain it, right? If you know how they are working, then you can explain it. Okay. Okay, very good. So in other words, now let's see the steps to implement the exec system call. Okay, so the of course first step is load the program into the current address space, new program that you are going to load it first, and copy arguments, right, into memory in the address space. That's the second step. And third step is you need to initialize the hardware, right? to start execution from the start of this new program, right? So these are the steps if you are going to implement the exec system call in your system. Okay, I hope you have understood it. Means we have actually illustrated 4 system calls. No, not 4, 3 I think. One is for, another is wait, then third one is exec, right? These 3 system calls we have illustrated. And you know the exit system call already, I hope. So exit is basically, it is the purpose of writing exit is to terminate your process, right? And so whenever you are going to terminate, basically if you are writing exit, it's a good idea to write the exit system call whenever you are terminating your process, because it will take the responsibility to do other things. For example, if you want to rip up some memory space corresponding to the process, then it will take care. So that's why writing exit at the end of your program it's a good programming habit, I would say. Okay. Okay.
Like that parameter in the exit system call.
Okay, so that's a good question. So in the parameter in the exec system call, it varies. So as I mentioned, there are various variant of exec system call. So you can, so of course you need to pass the command which you would like to run by the exec system call, right? For example, it might be the case you have some executable, that is ready, that you have created the executable, that itself you want to pass, right? Then you need to make sure that you are passing it properly, and there are various ways to pass it, and it depends upon the variance. For example, this is one variant, exec vp, and here basically we have a array of characters, right? So they are basically, we are passing in the first place, we are passing the command itself, and in the second place we are passing the second parameter, because this executable, whatever you have, wc, right, word count, it takes argument. For example, it wants to take the file or text, whatever you have, for on which you want to count, right? So that parameter you need to pass, that you can pass, use the other arguments or something like that. And the third parameter is null to indicate, okay, there is no other arguments, right? So there are several ways to pass argument to exec system call, and it depends upon other variants. So this is the simplest variant, exec vp, and this is the way to pass it. Okay. You
Actually,
just
I was asking
right.
about exit system call.
Right, exec. This is the exec system call, right?
No, exit.
Oh, exit. Okay, I see. So exit. Okay, so I think we write exit 0, right? Or exit 1. Okay, that you can see. So exit 1, when you are going to write exit 1 and when you are going to write exit 0, I forgot. Maybe in one case, when if error is coming, for example, right. So if error, for some error you are going to write exit, then we actually evoke exit 1. Otherwise, we pass, if let's say the program actually terminated, I mean, if you completed your execution very nicely, so then you can actually write exit 0. Okay. Oh, you are asking about exit, not exit. Okay, I did not understood. I thought you are asking about exit. So if you are writing exit, then basically, uh, so that also you need to see what are the parameters. As I mentioned, I mean, I didn't, I mean, here I am not mentioning in detail the parameter which you should pass. One is for, in general, we pass 1 to indicate there was some error, so I want to exit. Okay, for example here. And exit 0 means, okay, it was terminated successfully, and now you want to exit. Okay. Then if you are going to ask, I mean, if you are going to evoke this exit system call, then basically the operating system will take care that, okay, it will read that process, means it will clean up the memory, whatever it is used by the process, right? The process PCB also will not be there corresponding to that process. That thing will be taken care by the operating system, because there is the system call. Okay. Okay, any other question you have? So I think Dharmendra asked this question, right? Okay.
Yeah, no question.
Okay, no question. Okay, now let us see one example, means it's a case study only. Uh, so I hope everybody used shell sometime or the other. Is it the case, or you have not used shell? So you know shell, right? So for example, it is command prompt only. So there you have some command, right, or prompt, something would be there. There you can actually write some command like this, right? And if you, sorry, not LC, it's ls. And if you are going to do that, then you are going to see the result. Then after doing this, you will again see the prompt, right? There again you can type some command and you can execute that. Now the question is, how does this shell work? Or can you write your own shell? Can you create one piece of code that will be the same, that will be similar like shell? Can you create your own shell? Okay. So to do that, basically you need to understand how does a shell work. Okay. It's a very, I mean, basic thing, right? And it's very surprising that to write one shell on your, I mean, your own shell, let's say, it's a, it's not complicated thing. It's a very straightforward thing, and one can do using this system calls like fork, exit, and all. Exit, that's it. Wait, these are the only system call which you need to create your own shell. Okay. Okay. So now let's see in a basic. Okay, that you know, right? Right. So in your system, right, whatever the system you have, let's say it's a unique system. If you write, if you see the if you see the command prompt, all right. So that now the command prompt is basically it's a shell, right? So it's basically it's a child process, right? And who created that child process? The answer is init, right? So init is the only process which is the ancestor of all. So that process basically, if you see, because if you run your machine, and if you just write the command prompt, you search it, you will see the shell, right? Now the question is who created that shell, right? Which is the process? Who is responsible to create that process, right? So the answer is init. So init process is the process which actually created a child process, which is a uh, mm, which is some cell, right? And there basically you can type any command and you can run, right? Now the question is how it works. So inside your that child process, what you are writing, right, in the program, so that you can type any command and you can run it on your own. So any idea? Maybe I will get the answer from you rather than asking you. I mean, rather than giving you the answer, it's a good idea to ask you, and you guys should give me the answer. Any idea? So if you are going to create, so I hope you have understood what shell we are talking about, right? First of all, did you understand what is the shell we are talking about here? Did you understand? So how, okay, yeah. Hetvi, can you tell me something?
The shell as in the terminal for
Right.
Linux or a Unix system.
Right. Terminal only, right. That's the thing which I'm talking about.
So
Now let's say, if,
LS
right, so if,
lists files is like LS is a list
Huh.
of all
Huh.
files and
Files.
directories. Files
Like
in
if
the
you,
current directory. Yeah.
right. So if you write the command, then it will actually show you all the file list. It will give you the list of files and directories, right, under the current directory, right? Okay, just a minute. I think we got disconnected. Okay, is it visible now? No, right?
No.
Okay. Is it visible now? Is my screen visible?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, good. Okay, good. So, right now, my question was how, if you are, let's say, if you are going to write your code for the shell, right? You want to create your own shell, let's say, or your own terminal. Then what should you write over there? Any idea? What should you write? No answer. Okay. So basically, it's very straightforward, right? So basically, if you have ever used the terminal, as Hetvi was telling, right? So what shell does, it reads command from the user first, right? So after reading the command, so of course it is actually forking a child, right? That's the only thing it should do. Then, okay, once it is forking child, then of course it needs to do, it needs to execute that new command, right? Via using this new child process. And how to do that? Via using exec system call actually. You need to pass that command, whatever you read from the user, to the exec system call, right? So exec will be executed. Then in the from the parent process, you have actually created one child, right? After reading that command from the user. So that parent process should wait, right? It will wait until the execution of the child is done or finished. Then only actually it should go and read the next command from the user, right? It's just a while loop or something like that. So using very simple small code, you can write your own shell, right? Using this fork, exec, wait, and read system call. Just try to do this as a homework, okay? Or maybe you can implement your own shell in the first lab. That will be one lab assignment. Okay, that we'll see. Okay, but there are many more, many other things which you can do using shell, right? For example, if you write this, right, that is also permissible. So if you are writing this command in the shell, what you are supposed to get? Can anyone tell me what you are supposed to get? Any idea? Have you used such thing before? Any idea? Hetvi, can you tell me? No, right? Okay, so the only thing, so it's the only difference with ls. So,
Ma'am, it will
huh,
write
huh,
it
huh,
will
right,
write
right.
all the names of the files in this a dot text.
Right, that's the answer. Good. Thank you, Uddharsh, right? Your name is Uddharsh. Am I right? So yes, so the part, if you are going to write this command in your command prompt, then you will see that you will not see any result in the command prompt. Rather, if you open the file a.txt, then you will see all the results which you are supposed to see if you type ls command. Okay, so that is actually instead of writing in the screen, it is actually written to the file a.txt. Okay, if you want to do such kind of thing also using your small shell, what you are going to create, right? You also should permit this kind of behavior. So now the question is how you can implement such thing, right? There should be some mechanism. So until whatever we have discussed so far, we did not see how to do this, right? We don't have any idea. So let's see how to do that. So in other words, so you are going to execute something using exec system call, but the result of that exec system call, whatever you are going to, get, that you are not going to print in the standard output, right? In the print, in the screen, right? Rather, you want to write that somewhere else in some file, right? So how to do that? Okay, now let's see some example. Okay, so here what you can do. So basically, if you remember what we want to do, we want to we should close the standard output, right? Right, for that newly forked process, right? New process, your child process. Uh, by default, the output should be written to the standard output, which is actually nothing but the screen, right? So you want to close that, right? So once we close that, after we need to open some different file where you want to see your output, right? Let's say this is my output file, okay, where I want to see my output. So you open that, and this is basically it's if you automatically if you are going to do that, whenever you are going to open some file. So again, you will learn this when we are going to handle file system in detail. So basically, what it will do, it will, whenever we are going to open some file, right? So it will there will be some file descriptor, right? So that corresponds to this newly opened file, right? So now the question is, which file descriptor should it point to? And the first, whatever the file descriptor, whichever is open, means whatever it is not, it's not open, it is actually available. That file descriptor it should point to this newly open file. And here, since we have closed the first file descriptor, which is actually the corresponding to standard output file. So luckily, that file descriptor will be pointed to this newly opened file. Okay. So in this way, you can actually write whatever the result you have. Instead of writing in the screen, you can write it to the new some name file. So instead of p4.output, you can write here any file, a.txt also you could write. Okay. Then the rest of the code is actually same, whatever we had for the earlier program. Okay, you can see this. This is the same thing. Only the difference is we have closed the standard output and we have opened one new file. And luckily, the file descriptor of the standard output will be pointed to this newly opened file. So in other words, whatever after executing this new line, right? So this child process will not write the answer to the screen, rather it will write the output in some name file like this. Okay. Okay, so here also you can understand. So if you go back to the picture over here. Okay, so here basically if you remember, so what we mentioned that when we are executing this exec, right, then all the memory image of the parent process, means not the parent process, a memory image whatever you had for that child process, that is going to be replaced by the newly program which you are going to execute by this exec system call, right? Okay, that is the thing that is not changed over here also. But addition to that, if some file descriptor, whatever you had open over here or something closed over there, that thing, that extra thing will be actually carried forward to here. Okay, so that's why you can do this. So even if all the memory image is going to be replaced by the new process, when you are going to execute this exec system call, but the file descriptor and all, whatever you had for the previous, for your original child process, right, when it was created, those things, and you have changed it, right? So that change part is also going through, that is not changed. Okay, that thing is carried forward, even if you are going to write exec system call. Okay, so that's the beauty. Actually, you can change many things just before opening the exec system call. Okay, even if you are not permitted to write all these things after this, you can do such kind of things, means changing the file descriptors and all. If you do that, those changes will be carried forward to new memory image. Okay, that will not be vanished. So that's the extra thing which we have, and that's the beauty basically. Using this, you can now redirect your output to somewhere else, or maybe redirect your input also from somewhere else, right? Instead of standard input, you can actually redirect it from some file also. That is also permissible. Okay, I hope you have understood it. Okay, now you can see. So now let's say you are going to compile this program, and if you are going to run it, of course, you will not see any result, right? Since it is not writing anything to the command prompt. And if you want to see what is the output, then you need to open that file. Okay, then only you will see the output. Good. So I hope you understood this part. This would be useful when you are going to implement your own shell, okay, for the lab assignment. So we are yet to give you the set of lab assignments, whatever you are going to implement, right? That maybe you can hope in this week. Towards the end of this week. I think we have also class in this Saturday, right? So maybe on Saturday or before Saturday, you can expect. You may expect that. Okay. So do you have any question? Do you have any question? So that's the thing regarding the system calls related to process. So if we just want to summarize what we have learned today, so we have learned mainly so some APIs, right? Means application programming interfaces. In other words, system calls that is provided by the operating system to handle process, right? And what are those system calls? These are, to be specific, the most important system call is for, then exit, right? Wait, and exit is also there. Those are the main system calls we have, and how they are implemented, right, by the operating system. That also we have learned in detail. And this basic thing is actually it is important. So I would like to maybe I would like to, what should I say, ask you to run all the programs on your own. Maybe you can modify your own program and just see that. That's for the experiment purpose on your own, so that you understand it in more detail. Okay, there should not be any gap, because maybe you can write some program like this. Let's say I have a main, the inside main I have some let's say while loop, okay, and let's say I have for. So while maybe let's say I have some integer before that, some c is, let's say, is 0, and uh, c is, let's say, incremented all the way. So until c less than 10, so let's say I'm forking it. So how many process will be forked? How many process you will see in the system? So that kind of thing maybe you can try on your own. Okay. So if I run this program, how many process will be created? Any answer? If I am going to run this program, how many process will be created? Or let's say, instead of while loop, I am just writing something like this. For I equals to 0, I less than 10, I plus plus, okay, then just for, okay. So how many process will be created if you are going to do that? How many process will be created? Any idea? So just do all these experiment, okay. And of course, if you understand how fork is behaving, how fork is implemented, you will be able to answer this question. Okay. Any other questions? Do you have any other question? So just do this experiment. Otherwise, you will not learn it. Okay, if you don't do this experiment on your own.
Is it 55 its answer?
Okay, why?
Because in first iteration it will create a child process, and the value of I will be incremented to 1. Then the child process will run from 1 to 9. So it will have 9 iterations. So similarly, the child process created by child process will run 8
Right.
iterations.
Okay, right. You have understood it means. Okay, good. So yeah, that number I need to check, but but the way you explained it is correct, but need to check whether this is 5. Okay, sorry, 55. Okay, good. So I hope you have understood it and you do this experiment and all. Okay, so maybe in the next, I have some time, maybe 10 minutes times are there. So maybe, okay, how to utilize this time, right? So do you have any other question? Any question do you have? Because 10 minutes is more, right? So let me see. Okay, in the next class, what I am going to, we are going to discuss is basically simple thing. So, for example, okay, can you see this? I hope this is also visible to you. Okay, in the next class, we are going to learn, this is also going to be very important and interesting thing, the mechanism of process execution, okay? So means how you are going to execute some process. Maybe, right, quickly today we can illustrate one simple thing, right? So you remember this thing, right? How one process is executed. So whenever one process is executed, then you know that OS allocates its memory, right? Allocates memory and creates memory image, right? So this is the memory image which is created in the main memory corresponding to that process. That's the first step, right? Then basically you have the program counter and also stack pointer. Those should correspond to, so PC should correspond to here in some instruction, the starting instruction, and stack pointer should point to the top of the stack, right? So these are the very basic thing you should have, right? Then operating system is out of the process. That means out of the way, right? It is going to think, okay, now CPU is actually running the process. Operating system doesn't need to do anything, right? It should not do anything until and unless you understood you have something, some system call is there, right? So it means some privileged work needs to be done by the process. Then only the operating system should do something. Otherwise, the CPU should do on its own, right? Okay. In other words, this is the simple execution, right? First, operating system will initialize the thing, right? Then the program will run on its own, right? Once the program is done, then operating system, of course, you need to exit. You need to write the exit system call. Then operating system will free memory corresponding to the process and remove the entry of that process from the process list, right? That's the standard thing. This we have always, discussed this. Okay, now let us see what happens if you are going to invoke some function inside your code, right? I hope you know this already. This is nothing new. So you have some function, right? Sorry, here let's say you have evoked the function, right? And the function is defined somewhere else, right? It's a subroutine. It's written somewhere else. So whenever you are actually evoking that function, then that is nothing but some jump you are doing, right? The PC should be pointing to here instead of there whenever you are making this jump, right? And once this execution of this function is done, you should return back uh, the next instruction, right? So now the question is how you are going to implement it. And I hope you know this already. We do this via this stack, right? The stack pointer is that for that purpose stack is used, and stack pointer is actually for that purpose. So what we are going to do, so if we have some jump instruction like this, then the present program counter value, whatever you have, right? So that is going to be remembered here. So we are actually creating one frame in the stack, right, where we are going to remember these values. Okay. Then once this is done, then from that value, you can restore the program counter value and you can go back to your previous stage. Okay, so that's the purpose of the stack pointer, which is maintained by for every process you have one part which is known as stack, right? That we already mentioned it, and that is the main purpose for doing this. Means to help that inside that function also you might have several function calls, right? So recursively you might have called that function again, right? So in other words, you have the stack is grown. Now, if you want to return back, then you need to pop from that stack. Then you can go back, right? Right? That's the basically beauty of the stack. Using stack, you can handle function call, right? Now the question is, right? So now the question is, as I mentioned, right, today itself we mentioned there is system call, which looks like function call, but it is something different from the function call, right? So can you tell me what would happen if I instead of some function, if I am evoking some system call, for example, let's say I'm evoking one system call for, then how would you manage such thing? Are you going to remember the the old value of the program counter in the stack frame of the user space of the process itself? Means each process has some user space, right? Means it has some memory image in the main memory, right? So there are you going to know corresponding to that stack? Are you going to remember it, or how it should differ, right? Are you going to rely on that? Any idea? So how this would be different from the system call? So system calls are different, though they looks like function call, they actually different. So here is the answer basically. So basically, okay, I think we will not be able to finish that. Maybe so to motivate you, you can think on your own also. So the question is, I hope you have understood it. The question which I asked is, if you understood how functions are evoked and how function calls are actually managed by using the stack pointer, right, or using the stack in the address space, right? You have the address space corresponding to each process, right? There you have a stack part. So that stack part is actually handling the function call. Now the question is, if you have a system call, there should be similar mechanism, right? Because system calls are nothing but some kind of function only, right? But those functions are actually not part of the your user code. It's part of the operating system code, right? That function is basically defined somewhere in your operating system code, right? So that's the main difference, and those are privileged kind of thing, right? Now the question is, what should be the mechanism, right, to handle those kind of calls, right? Okay, think about it. In the next class we are going to discuss that, what are the mechanism to implement some system calls, right? What should be there, what are the difference with function calls and all. Okay, with this maybe we can conclude today's session. And okay, I of course, if you have some question or something like that, if you would like to discuss, then you can ask me. Any questions? Do you have any questions? So in other words, in the next class we are going to see these in details. Okay. Mechanism for process execution, which includes how to handle system calls, and this already you know, so I will not illustrate on that. And of course, so and one extension of this is basically how, if you have, let's say, several process, right? Of course there should be some mechanism to context switch in between the processes, and what are the mechanism to do this context switching, right? There should be some code corresponding to your operating system which would handle this, right? So we are going to learn this in the next class. Okay, do you have any other question? Any question? Okay, if you don't have any question, maybe we can conclude today's class. Okay. No question, right? No question? Okay. Okay, then thank you. See you. Okay, our next class is on Saturday, I think. We'll meet on Saturday.